In this section, we will discuss how to solve so-called separable differential equations. So definition 1 says what a separable equation is. If the right-hand side of the equation dy dx equals f of xy can be expressed as a function g of x that depends only on x times a function p of y that depends only on y, then the differential equation is called separable. So we have that f of x is equal to g of x times p of y. If that's the case, we call this separable. So let's do a quick example where we showed that dy dx equals 2x plus xy over y squared plus 1 is separable. So we need to look at this right-hand side, and what we can see here is that 2 times x plus x times y over y squared plus 1. So I'm putting x in green here. If you look at the numerator, you see that both terms have a factor of x. And so that is a factor that I can factor out. And so I have x times, and then what I'm left with here is 2 plus y, and then all of this is over y squared plus 1. And I can then write that as a product as follows. So this is x over 1, or simply x, times 2 plus y over y squared plus 1. So this second function is our function that depends on y only, and the first part is our function g of x. And so it's separable because we've written the right-hand side as a function of x only times a function of y only. So now let's talk about the method for solving separable equations. So to solve an equation dy dx equals g of x times p of y, we're going to multiply both sides of the equation by dx. Now, that seems a little bit iffy because dy dx is a notation for the derivative of y, and it does not literally mean dy divided by dx. But I will show later that this makes sense. So just think about dy divided by dx, even though that's not entirely correct. But if we then multiply both sides times dx, right, and we multiply that by dx, then the dx's, we can think of them canceling out here. And then we're going to multiply both sides by 1 over py, or we can think of that as dividing by both sides by py, p of y. And so we're left with 1 over p of y dy, and if we call 1 over py h of y, On the left, what we're left with is h of y dy, and on the right hand side, the py's cancel out, p of y, and so we're left with g of x dx. Then what we're going to do is we're going to integrate both sides. And so we can integrate a function of y with respect to y, integral of h of y dy equals the integral of g of x dx. And if we call the antiderivative of little h capital H and the antiderivative of uh, little g capital G of x, we can write this as capital H of y equals g of capital X, g of x plus c. And there's a constant of integration here on the left, and there's a integral of a constant of integration on the right. We can think of this as c1 and c2, but then by subtracting c1 from both sides, you just get one single constant of integration. So this last equation then gives an implicit solution to the differential equation.